Today, we're diving into one of the biggest questions there is, and we're going to look at it through the lens of a new theory that might just change how we think about life itself. Let's get right into it.
I mean, really think about that. You've got a bunch of molecules floating around, and then suddenly it's alive. Where is that line? At what exact point does a random chemical soup wake up? It's a question that has felt almost impossible to answer for, well, forever.
For the longest time, the search for life's origin has kind of felt like a big detective case. Scientists have been chasing different leads, focusing on a few key, usual suspects that they thought might hold the answer.
And you basically had two main camps. On one side, you had the metabolism first folks. They were convinced that life started as these self-powering chemical engines. Then you had the RNA first team, who believed it all kicked off with a special molecule that could copy itself, kind of like the first tiny blueprint. Here's the thing, though. Neither side was totally wrong. They each had a critical piece of the puzzle, right? You absolutely need metabolism's chemical networks. You for sure need something like RNA to carry information. And you've got to have some kind of container, a boundary, to keep it all together. But by themselves, none of these pieces could show us the whole picture.
And this is where things get really interesting. What if we've been looking at it all wrong? What if the secret to life isn't about finding one magical ingredient? What if it's all about the system, about how all the different pieces are arranged and how they talk to each other?
And that brings us to this new idea called constraint resonance emergence theory. Let's just call it CRET. It suggests that life didn't begin when some specific molecule appeared. No, it began with a sudden, sharp shift in organization. It's all about how different parts of a chemical system, working at different speeds, suddenly lock into a powerful, self-reinforcing feedback loop. This quote from the research really nails it. The theory says it's not about the stuff itself, but about the math of the whole system. Life kicks in the moment that feedback loop gets strong enough to sustain itself. So to really get this feedback loop, we need to break it down. Crate says any pre-life system has three main layers. And the key thing is, each one operates on a totally different timescale, from super fast to really, really slow. Let's use an analogy. Down at the bottom, you have the microdynamics. These are just the individual, lightning-fast chemical reactions happening all the time. Think of it as random background static or noise. Then, in the middle, you get the mesonetworks. This is where some of that random noise starts getting organized into self-reinforcing patterns. This is like a microphone that starts to pick up and amplify that noise. And then at the top, you have the macro constraints. These are the big, slow-moving boundaries, like a cell membrane. This is the speaker, which projects that organized sound back out. So the first part of the loop is what we call upward amplification. This is the microphone, the chemical network, capturing all that random noise from individual reactions and starting to turn it into a structured signal. Randomness is starting to become order. But this is the genius part: downward selection. The speaker, that big boundary, doesn't just play the sound. It actually feeds back and changes which noises the microphone picks up in the first place. The large structure actively selects and stabilizes the tiny reactions that are useful for building and maintaining that very structure. And when you put it all together, you get this. The fast reactions build the networks. The networks help form their own slow-moving boundary. And then that boundary reaches back and reinforces the very reactions that created it. The system literally becomes its own cause. It's a closed loop. Which, of course, brings us right back to the big question. If life is just this closed feedback loop, what's the actual trigger? When does the switch flip from just a complicated chemical process to something that's truly alive?
Well, according to Crete, the answer is a number. Just one. That's it. The entire massive transition from non-life to life comes down to hitting this one simple number. This is what's called the unity gain threshold. It's pretty straightforward. If the power of that feedback loop, its gain, is less than 1, the system just can't keep up. Any organization that appears will just fizzle out and die. But the moment that gain hits 1, or goes even a tiny bit higher, the system's ability to build itself becomes stronger than its tendency to fall apart. It becomes self-sustaining. It becomes autonomous. It is, for all intents and purposes, alive. And when a system crosses this line, it's not a small thing. A whole bunch of properties we associate with being alive just emerge all at once. The system can suddenly maintain itself, it can handle being bumped around a bit, and it even gains the ability to evolve. The boundary and the chemistry inside become true partners, constantly shaping each other.
So what does this new way of thinking mean for those old debates we started with? Well, the cool thing about Crete is that it doesn't say they were wrong. Instead, it gives us a new framework that kind of shows how they all fit together. This really reframes the whole conversation. That old fight between metabolism first and RNA first, Crete says they're just two different ways a system could get its feedback gain up to one. The argument about whether the network or the container came first, just different ways the loop could have closed. And that question of whether life started gradually or all at once, the answer is both. It's a gradual buildup of complexity that then hits a tipping point and leads to a sharp, sudden transition.
And that leads us to a really, really profound idea, which this final quote captures perfectly. If this is right, then life might not be some 1 in a trillion cosmic accident that only happened here. Instead, it could be a predictable state of matter, a natural transition that can happen in any chemical system that's complex enough.
So if life is defined not by its specific parts, but by its organization, by its feedback loop hitting that magic number 1, that completely changes how we should look for it out there in the universe. We're not just searching for a particular molecule anymore. We're searching for a particular kind of dynamic harmony. Which leaves us with one last huge question to think about. Where else out there might chemistry be singing the same self-sustaining song?